Okay, today's lesson is about the idea or introducing sampling distributions. We're also doing an activity in A-Lab this week about with pennies that's also talking about sampling distribution. It's a big idea that will be important for this, really for the semester. So the idea of sampling, it's kind of a tough idea to get to, but this is the homework from last night. Okay, this is kind of, you're going to see a lot of review in this lesson, a lot of stuff that you've seen before. We've talked about parameters and statistics before, if you remember, the alliteration there. Statistic comes from a sample, parameter describes a population, PP, SS there. You might remember this when you're talking about means. The Greek letters are the population parameters. The non-Greek letters there are the sample statistics. X bar is what we call the mean, where mu is the population mean. Sample proportion is p hat, the predicted there, and then p is the actual population proportion. Sx is the sample standard deviation, and then sigma is the population standard deviation. I usually see the sample mean as lowercase x bar, but I guess the formula sheet at one point does use uppercase x bar. Means the same thing. Okay, so let's look at this example. A Gallup poll asked 550 randomly selected U.S. adults if they believe in ghosts. Kind of an interesting question. Of the respondents, 160 said yes. What is the population? So the population would be of selected U.S. adults, so all U.S. adults, right? That's everybody. What is the parameter? So the parameter describes the population. So that I think we're looking for what percentage of U.S. adults believe in ghosts. The proportion of all adults who believe, U.S. adults who believe in ghosts. So be very specific. Notice they paired it back, the population there, of all U.S. adults. It's tempting just to say of all adults or something, but we want to be specific here as much as possible. What is the sample? So the sample is the 160 respondents who said yes. The sample is the 515 randomly selected U.S. adults. And then the statistic would be the 160 out of 515, or 31%. That's the actual proportion who say they believe in ghosts. So we took a sample of 515 out of the entire population of U.S. adults. Let's try it again. During the winter months, the temperature outside the Starnes family cabin in Colorado stays well below freezing for weeks at a time. To prevent the pipes from freezing, Mrs. Starnes sets the thermostat at 50 degrees. She wants to know how low the temperature actually gets in the cabin. Oh, that's interesting. So you set the temperature, the thermostat, but it could actually be colder or warmer than that. We don't really know. So a digital thermometer records the indoor temperature at 10 randomly chosen times during a given day. The minimum reading is 40, so that's the lowest it goes. What's the population? So kind of weird. It's not really a group of people here, right? So this is the population would be the indoor temperature at the Starnes cabin, I think. Oh, okay. So population is all times during the day in question. The parameter is what are we trying to measure about that? We're trying to measure the indoor temperature at all times, the true minimum temperature. Okay, that wasn't clear from the question. They should have clarified that. They were looking for the true minimum temperature of the cabin at all times during the day. We don't know if that's 40 degrees, right? We're looking for the true minimum. I guess they said that when they said, how cold will it get? No, they didn't really say that. How low the temperature actually gets in the cabin. So they did kind of say what the parameter was there if you read it carefully. The sample would be, let's see, they took 10 randomly chosen times. That should have been a key. So when you look, sometimes when you're having trouble identifying the population, if you look what the sample is, in this case, that was kind of clear. It was the 10 randomly chosen times. That would have helped you go, oh, the population is all the times during the day. So I think sometimes seeing the sample helps you go backwards and understand the population. And the statistic would be the minimum temperature from those 10 recorded times, which was 40 degrees. Okay, so in this case, like it's hard to, we don't use a lot of symbols for this because we're talking about minimum temperatures. There's not a symbol for that. And so what they're saying is when you talk about population, notice they said the word all times during the day. All or true describes population. Whereas the word sample there describes, when using a statistic. So in the population parameter, they use the words all and true. That indicates that's talking about the population there. Yeah, I mean, this definitely happens. Sometimes students refers to the sample instead of we're trying to estimate the population because they're not clear about the wording. So when you're talking about population, use words all or true, and for statistic, use the word sample. Okay, we've talked about at least the first idea. I think we talked about both ideas to some degree here. So sampling variability, if you flip a coin 10 times and then flip a coin 10 times again, you're probably going to have some variability. But you're probably not going to have the same number of heads both times because variability happens, right? That's what sampling variability is. Sampling distribution is the list of all possible sample size of the same size from the same population. We're going to show you an example of that in a minute. This is a big idea of this lesson, I feel like, the sampling distribution. What is it? So here's an example. Here's an example of the proportions of 50 samples of size n equals 20 from a population. So this is not actually a true sampling distribution. This is getting at the idea of a sampling distribution. So p hat represents the proportions of sample size n equals 20. So for sample proportion of pennies with shields on the back. There are some pennies that actually have a shield on the back. Now I'm curious, I need to look. Let's see. So I guess maybe the newer pennies have that because I feel like the older pennies don't have shields on the back. When I was growing up, I don't remember that. So I'm guessing the new ones do. The sampling proportion of pennies with shields on the back. So it looks like around 60% on average of pennies, if you kind of grab a random penny, have shields in the back. But sometimes they took some samples of size 20 from this group of pennies they have, this pile of pennies, and one had 90% had shields in the back, and one had 30% shields in the back. So 30% of the 20 that they chose had shields on the back. So you can see there's a whole wide distribution there. I don't think this is it doesn't indicate that this is all of the possible sample sizes, what a true sampling distribution would be, which every possible sample of that size, in this case of size 20, there'd be a lot more probably dots here. Each p hat's kind of like a dot on a dot plot there. They just use p hats to help you understand each one of those is a sample of 20. It's the mean, it's a sample of 20 there. Okay, John and Carol have 4 grown sons. So first thing I want you to do, let's just find their average height. So if I add those up, 71 plus 75 plus 72 plus 68 divided by 4, 71.5. So the average height of their sons is 71.5. That's the population average height, if that makes sense. Now, for some reason, instead of actually just finding the average height, would be pretty easy to do of the population, because we know the whole population, we're going to take samples of size 2, and in this case, all 6 possible samples of size 2. Okay, so let's see. So we could choose like the 71 and 75, those are the first two choices. 71 and 72, first and third, 71 and 68. Those are all the ones that start with 71. I'm going to start now with 75. 75 and 72, 75 and 68. Those are all the ones that start with 75, and then 72 and 68. And I don't think order matters here when you're choosing every possible case. So it looks like we have 1, 2, 3, 4, 5. There are 6 different possible groupings of sample size n equals 2 from this population. I listed them all out. We would have to calculate the mean height in each sample. So, and that would be pretty easy to do. Whoops, be pretty easy to do. So if you wanted to calculate the mean, like the mean of these two would be 73, the average of 71 and 75. This would be 71.5. This would be, I think, 69.5. This would be, I think, 73.5. Do this in my head, so it could be making a mistake here. 7, so 3.5. So I think that'd be 71.5, and this one would be 70. So now we have those 6 black numbers. Those are the averages of each one. I think they did this for us, is my guess. Yeah, they got those 6 sample means there. I'm sure their work is correct. Mine might have been correct. The table where it's all combinations of heights. So that's called the sampling distribution. And that is the true sampling distribution because the key word there has all possible combinations of sample size 2 of the suns. And they took the mean of each one of those groupings. So all 6 of those, they took the mean. They sometimes will ask you to plot this on a dot plot. So here's what those 6 means plotted on a dot plot look like. It looks very symmetric, by the way. It looks like the average is going to be 71.5 because they're all perfectly symmetric around 71.5. And by the way, that was the actual population mean, if you remember. So the mean of the sampling distribution should be the same as the mean of the population. So that's really nice, actually, that kind of works out. Be specific when you use the word distribution. There are 3 types of distribution. So one type is just the distributions of height in the population. In this case, there were 4 in the population. That's the distribution of height of the population. You could take, we took 6 samples of that of size 2. One of them was a mean of, one had 71 and 75. So those are 2 of the heights that we chose. The average was 73, if you remember, on that one. But that would be a distribution of just 2 of the heights. Distribution of the sample age of height for all possible samples. That's called the sampling distribution right there, right? So that would be of the range. This is for 6 possible ranges. So that if you took those 6 cases and found the range of each one, this would be the sampling distribution of the range, which is a different statistic, but it's the same idea of a sampling distribution. Whereas the first 2 were just distributions of heights, one of a sample and one of the population. So I think that's a good idea to say, don't just say of the distribution, but of the distribution of blank, like fill in the blank. What is this distribution? Is this of the sample, of the population? Is this the sampling distribution? What is this? Okay. I've determined how much homework time students will get in class. Mrs. Lynn has a student select a simple random sample of 20 chips from a large bag. The number of red chips in the sample determines the number of minutes in class that students get to work on homework. Mrs. Lynn claims there are 200 chips in the bag, and she says 100 of them are red. Okay, we'll see. When Jenna selected a random sample of 20 chips from the bag without looking, that was important, she didn't just look for non-red chips or just for red chips, she got 7 red chips. She just happened to get 7. Does this provide convincing evidence that less than half the chips in the bag are red? I don't know if it's convincing or not. It does provide some evidence. You would have expected, I guess, the average if you did this many times, would be 10, right? We think about half of the chips are red. And if you grab 20 chips, you would expect 10 red chips. She got 7. So there might be some evidence that less than half the chips are red. What is the evidence? Well, 7 divided by 20 is, 35%? So that is less than 50%. So there's some evidence there, but we don't really know if it's convincing evidence or not, right? So we might have to do a simulation or something like that to do that. So that's the same thing. Provide 2 explanations. So one explanation could be just like, what do we call that? Sampling variability, right? I mean, she just kind of luck of the draw. She's telling the truth. Jenna just got, because there's going to be some variability when you take a sample. 35% doesn't seem that unusual. It's hard to see how unusual that is, but it doesn't seem too extreme there. And so maybe it was just sampling variability. I think the other possibility is maybe Mrs. Lynn is not on the up and up. I hate to say this about Mrs. Lynn, but maybe she's not telling the truth exactly about how many chips are in the bag are actually red. She doesn't want to give as much time to students to do their homework in class. Okay, so they use technology to simulate choosing 100 simple random samples of size 20 from the population. So this is not a true sampling distribution because it doesn't say they took all possible samples of size n equals 20. They just randomly collected a bunch of them, 100 of them, but there might be, my guess is there's quite a bit more than just 100 all possible ones. But that's nice. They plotted those on the chart below. So this is the simulation they did. They did a simulation, they did it 100 times. They took a sample size 20, they measured the proportion of red chips in there. You could see like right there on the top end there, one time they got 80% red chips. It's kind of amazing. On the low end, one time they got 25% red chips, right? So there's a pretty big range between 25%, 80% there. But quite often they got around 0.5. So that's actually, when you look how symmetric that is, you're like, yeah, I'm thinking she's probably telling the truth, but maybe not. I don't know. What is that dot? That is one simulated simple random sample of 20 chips where there were 16 red chips, or 80% of the chips were red, which is kind of a lot, right? Seems kind of like a lot. Would it be surprising to get a sample proportion of 35%? Remember, that's what the proportion was. Let's compare it to the simulation. 35%. How extreme is a result of that, or even more extreme? So how many, if you have to count the dots here, so 35%, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I counted 8 in that at 35%, 2 at 30%, and 1 at 25%. So 35% or more extreme. I counted 11 out of the 100 dots. So about 11% of the time. 11% super unusual. Is it less than 5%? I don't think so. Right now, from this one sample, I don't think we have enough evidence to say that this teacher is lying. And so that's, is there convincing evidence that less than half the chips in the bag are red? There isn't convincing evidence, right? Because it was 11% of the time that's going to happen by chance alone. So I don't think there is convincing evidence. We've got a couple sample problems here that might be helpful. The U.S. Census Bureau defines the East Central region of the United States as Illinois, Indiana, Michigan, Ohio, and Wisconsin. I didn't know there's something called the East North Central region. Of these states, only Illinois, Ohio, and Michigan have at least 15 electoral votes. I guess those are the larger states of those. They have at least 15. List all 10 possible samples, simple random samples of size n equals 3. So I'm not going to do all of them, but I'm going to start it just to make sure what we're saying. So let's just say I chose the first 3 listed. I'm guessing they're alphabetical order. So I chose Illinois, Indiana, and Michigan. So if I chose those 3 states, how many of those have at least 15 electoral votes? So Illinois is one of the bigger ones, so it does. Illinois, Ohio, and Michigan. So, not all of them. So 2 out of 3 of those 3 randomly selected states, if I'd done that randomly, have at least 15 electoral votes. And so then you would choose another grouping of 3 and figure out how many of those have that. List all 10 possible simple random sample sizes, so SRSs. So there's 10 possible cases here. You can see the 10 there listed off to the right. We did that first one there and we got 2/3 as well. And so they did every possible case there. The lowest percentage you get there is 33%, 1/3. And there's probably one case, there is, where you pick all 3 big states there, and 3 out of 3 is 100% there. So they plotted those on a dot plot. That's what the dot plot would look like. You can see it's pretty common to get 2/3 of the states with 15 electoral votes. If you choose 3 of them, you might get unlucky, only get 1/3, and you might get really lucky and get 1. All of them have at least 15. Okay. This is kind of a longer question, has a lot of parts to it. I just showed the first 2 right there. Let's see if this helps us kind of understanding the simulation and how to use it. The packaging on Snickers fun size bars claim the average mass of all bars is 17 grams. All candy bars have, the list of how much it's supposed to weigh. To investigate the company's claim, a statistics class collected a random sample of 40 Snickers fun size bars. We couldn't do that here at St. Mary's because the peanuts thing. But evidently at the school they could. The average mass of the sample is 17.28. Okay, well that's actually encouraging, right? That's more than they're saying, and I'm okay with that. I'm okay with a company providing, they say, hey, there's 17-gram bar in here, and they give you a little bit bigger bar. That's a nice bonus. Does this provide convincing evidence that the mass of all Snicker fun size bars is greater than 17? Ooh, okay. I don't know, to provide some evidence. What is the evidence that the average mass is greater than 17? Well, from a random sample of 40 Snicker bars, the average was 17.28, which is larger than 17. So that's one way. That's definitely an example. At least some evidence. Provide 2 explanations for the evidence described in Part A. So maybe this is just the result of sampling variability, right? There's going to be some variability. If I chose a different sample, 40, maybe you get a different result there. So it could just be chalked onto that. Maybe this company really is packing more than 17 grams into every candy bar there. And that's actually pretty possible because my guess is they don't want it to cut it too close to 17. They probably want to, because I'm sure the FDA has some rules that if you certain percentage time keep providing less than what you're stating, that would be bad. So my guess is their average is over 17. That's just a guess. So it's possible the packaging is incorrect and the mean mass is actually larger than that. Part C, so they actually did a simulation. So they used technology to do samples of size 40, and they found the mean of each of those samples of size 40 for 100 simulated samples. This is not the full sampling distribution because they only said 100 simulated samples. They didn't say every possible or all samples of size 40. And I think there'd be a lot more than that if that was the case. There's one dot at 16.72. What does that mean? That means in that particular simulated sample of 40 Snicker bars, 16.7, the average of that particular simulation was 16.72. In one simulated simple random sample of 40 bars, the average mass was 16.72 grams. Would it be surprising to get a sample mean of 17.28? Remember, that's what we got a minute ago. How surprising is that? So 17.28 or more extreme than that. I only see one dot, honestly, that's bigger than that. So 1 out of 100, there's a 1% chance. Yeah, it would be surprising. There's only 1% chance. Only 1 out of 100 dots in the simulation had a greater mean than 17.28. So yeah, that would be very surprising. Based on your previous answer, especially that last one, is there convincing evidence that the mean mass is greater than 17? Absolutely. Is there only a 1% chance that our sample happened? Yes, we have convincing evidence because um, because of the 1% chance we found. That's your lesson for today.